All right. Abstract algebra. So. How's it going? All right. Cool. I actually went into Dr. Dunaway's econ review session last night and gave him a little Craigasm. I felt a little bit bad about it, but not really. Memes. Memes bring us all together. Or something like that. Alright. So I'll let some people arrive, but I just wanted to give a little reminder here that your project outlines are due by the end of the day Monday. So roughly midnight, 59 p.m. Monday. So I have one email I need to respond to about an idea for someone, and then other than that, if you have questions while you're looking through things, if you haven't been able to find more sources after your first one that you turned in and would like some guidance, I can provide that. Or if you would just like some general guidance on okay, I have all of this information, I could write a 30-page paper, how can I make this 6 pages, what should I focus on, I can help guide that as well. So definitely make use of me. I imagine you're focused more right now on the problem set, so after you're done with that, feel free to talk to me on Discord or via email about your project. I'm more than happy to help. Okay. Any questions on stuff before we get started? Seemed like the Cayley's theorem thing we will talk about. But the first part went pretty well for today. Okay. So, I'd like to start by having some participation from you guys here, right? So, we had to write these as products of transpositions. So we had 3, 1, 5, not necessarily adjacent here, right? That's kind of the next step. So we had 3, 1, 5. We had 2, 4, 6, 8. How do we write these? What are some ways? There are probably 2 common ways that you will see this broken down into transpositions that are not adjacent, and this kind of helps guide you for a general process in 493. So what did you guys find for these 2? Yeah, so this is 1, 3, 1, 1, 5. Did anyone get something different than these? I don't know why I put equals on the first one. Yes. 4, 6, 6, 8. Anyone get something different? There's kind of one other common way. I know at least a couple people used it. I'm not sure if they're maybe here yet. Okay. Well, if someone else comes up with something here in the next couple minutes, I mean, first let's just talk about how this actually works, right? So this is a nice little pattern. You kind of see what's going on, right? You're just kind of bridging the gap between them. And so, you just see 3, 1, okay. Then I keep that 1 and do 1, 5. Why does this work? Well, we see that 3 is going to 1, and 3 is not in the second one, right? So 3 only shows up here, 3 goes to 1, 1 goes to 5, and then 5's not here, so 1 goes to 5, and then 5 goes to 1, which goes to 3. So this is accurate. Another way, well, it's easier to see on the next one. So yeah, this is the same pattern, right? Just 2, 4, 4, 6, 6, 8. You just kind of step up the ladder, if you will. But remember to read them from right to left. Another way you can write this is 2, 8. 2, 6, 2, 4. Basically, you can fix your first guy, right? You have the 2 showing up in all of them. But then, remember, you're reading right to left. So what this does is it sends 2 to 4, which is what you want to do. 4 no longer appears. Okay, so that means it stays at 4. Okay, then I look at 4. 4 goes to 2, and then the next one sends 2 to 6. But then 6 doesn't appear to the left, so 4 has gone to 6. 6... well, it doesn't show up in the first, it shows up exactly here, it goes to 2, and then it goes to 8. So this is another common way. So basically you have a couple of options there. And then putting them together, well, you just put them together, right? They're disjoint, they commute, like they don't affect each other. And so, you can write this as 3, 1, 1, 5, 2, 4, 4, 6, 6, 8, or you could try to do the other thing. So this guy, right, using that same method would be like 3, 5, 3, 1, right? Fix your first guy, go to the last one, then you kind of go back to the left. So you could also write this as like 3, 5, 3, 1, 2, 8, 2, 6, 2, 4. What'd you come up with for D? Can you come up with both ways here? So I want to see 2 different ones using what we just talked about. I know the delay isn't that bad. And there are 12 people. Okay, yeah, so that's the first one, kind of using the method we talked about first. So what about the second one? So 1, 6 is already a transposition. So using this second method, how can I rewrite 2, 5, 3 in a way that is not 2, 5, 5, 3? So what did I do up here? 2 went to 8. That one went to the left. 2, 6. There. 2, 4. There. So I should be doing 2 goes to 3. That's like the one that goes on the left. 2 goes to 5 here. Yeah. Yeah. Although, I would write 2, 5, but yes. Yeah. Exactly. Okay. So then what is our general pattern? So if we have some k cycle, Alright, so this is, what, 493. So if you have some k cycle, we have like two ways we can naturally break it down into not necessarily adjacent transpositions. So the one you guys seem to be suggesting is, well, we just build it up. A1, A2, A2, A3, we go all the way to AK minus 1, AK. And then the other one you can do, and again, this is personal preference, and I saw, I think, 2 of the second and 4 of the first when I was reading through this morning. So this one, right, again, you have A1 showing up in all of them. And the idea is to start over here, and you know you want A1 to go to A2. Your next one then should be, maybe I'll even put one more in here. Well, you don't want to affect A2 again, but A2 would go to A1 here, and then you want to send A2 to A3. So then A1 goes to A3, and then you back it up to A1 goes to AK minus 1 here, and then finally A1, AK. Okay. So these are your two kind of standard methods. Either one works, personal preference. But this allows us to break down any cycle into a product of transpositions, and therefore any product of disjoint cycles, right? Which we can always do for any permutation. We can write as a product of disjoint cycles, and thus we can get all of those individually written as products of transpositions, put them together, and you just have a longer product of transpositions. So that's great. But in general, right, these are not adjacent transpositions. So let's think about this through an example here. So how do we do adjacent ones? So let's just think of something simple like 1, 4. We talked about this a long time ago. This was what we talked about with 2, 8. We were able to do just adjacent swaps. Does anyone remember we talked about like climbing and descending? We had a little algorithm for doing this. Does anyone know how to write 1, 4 as a product of adjacent transpositions, ones that are only one apart? Yeah, this is the notion of climbing and descending that I was talking about, right? So we see this 1, 2, 2, 3, 3, 4, 2, 3, 1, 2. So like what's going on here? Well, we're climbing, right? So again, it's going right to left. So we climb up to here. We're climbing 1 up to 4. But the problem is along the way, right? We sent 1 to 2, 2 to 3, 3 to 4. Awesome. So 1 went to 4. The problem is 2 went to 1. And then 1 doesn't show up again. So I need 2, 1 to be multiplied by 1, 2 to get 2 back to itself, right? And so that's why I have this over here. And similarly, right, so 3 goes to 2, and so 2 needs to go back to 3 over here. And so this is the notion of like you climb up to 4, and then when you go back down, you're kind of switching the other guys back, right? So like this process, if you look at it from right to left, right, so we have like 1, 2, 3, 4. I don't know why I'm doing it this way. I don't want to have to write circles every time. So you have 1, 2, 3, 4, and so the process, right, is you just switch it. So it's 2, 1, 3, 4, and then it's 2, 3, 1, 4, and then it's 2, 3, 4, 1. So we got 1 in the right place, right? So that's up to here. But then we need to switch them all back. And so we basically switch these two back, we switch these two back first. So then we go 2, 4, 3, 1, right? So we got 1 in the right spot. Now we're getting 4 in the right spot. We're bringing it down. We're descending. And then we switch these two. And so we get 4, 2, 3, 1. Okay, and so this was doing 1, 2, 2, 3, 3, 4, 2, 3, 1, 2. And so 1 climbs to 4, 4 goes down to the first spot. Or whoops, sorry, I guess that's here. There we go. Okay? Does that process make sense? I think the picture helps. I think it helps to see like what you're really doing there. You're just switching them one by one, you're moving your thing to the right, but then you have to move the one that was on the far right back down to the left. So you have to like switch them all again. Questions? Okay. Well, so what's the general process then? Right, so if I see it in general, AB, I want to think of this as like what I did with 1, 4, right? So first, I'm going to get A to B by switching one by one, right? So I start over here on the right, I go to A plus 1, I go A plus 1 to A plus 2, I go A plus 2 to A plus 3, all the way until I get to B, right? Whoops, that's just B. So this is me climbing A to B, and then I need to send B goes back to position A, right? And so now I just do my descent. So I do B minus 2, B minus 1, all the way down until I get to A plus 1 again. And notice what you're really doing here, if you want to think in another fashion, since we've talked about conjugation, right? You start with this B minus 1B, you then conjugate by B minus 2, B minus 1. You then conjugate by B minus 3, B minus 2. B minus 2. And you keep conjugating until you end up conjugating by A plus 1. And remember, this is really conjugation because these are transpositions. They're equal to their own inverses, so that's why I don't have inverses showing up here. So that's another way to think about it. So does that process make sense? You guys are quieter today, even via typing. Okay. Cool. All right. So then the application of this is that we can write any permutation first as a product of any transposition, well, specific transpositions, but general transpositions, not necessarily adjacent ones. And then we can further break those down and write it as a product of adjacent transpositions, right? So that was 495, and it basically followed immediately from this, right? So if you start with some general sigma in Sn, then you write sigma as a product of disjoint cycles. We can always do this. Then you use 493 to write each cycle as a product of transpositions. And hence, your sigma, being a product of those cycles, is a product of transpositions. And then if you want further to use only adjacent transpositions, then you use 494 to break those down into products of adjacent transpositions. Okay, so essentially we have now shown that we can generate, right? Because I mean, we're just writing as a product. So I mean, what we've really done is just written Sn as being generated by either the set of transpositions or even just the set of adjacent transpositions, right? And one of those is bigger than the other, right? So Sn can be generated by all transpositions. And of course, you don't want to like double count, so you can really assume that A is less than B here, and that these are both between 1 and n. But there you have a lot of things, and so this is one reason it's nicer to have just the adjacent transpositions. That's equal to, and this is not equal to n. Right, so for this one, you know exactly how many you need. This is a nice little generating set of exactly n minus 1 elements. So you need n minus 1 elements to generate Sn. You can actually do it with fewer, but we're not going to talk too much about that. But basically, you actually only need 2 elements to generate it if you take an n cycle and 1 transposition. So for instance, 1, 2, and 1, 2, 3 down to n will generate Sn as well, but that's not something we really proved here. Okay. But not 2 transpositions. Yeah, definitely not 2 transpositions. Yes. Unless it's, yeah, S3. S3 you can do with 1, 2, and 2, 3, but that's in this case right here. Cool. All right. So Cayley's theorem. I wrote the start of this just because I didn't want to draw the group table and take up a whole bunch of time in class. So let me just switch over to this. So I basically wanted you to look at 2 different ways to view D3 acting as a set of permutations, right? So Cayley's theorem in general states that any group, so let's get a little vocab here first, so maybe I'll go back. So Cayley's theorem, what's the general statement? Well, first we need this definition. So a permutation group is a subgroup of a symmetric group. Right, so it doesn't have to be like Sn, it can be a subgroup of Sn, which may not be like Sk for some smaller k, right? So that's the reason we introduced this. And then Cayley's theorem states that any group G is isomorphic to some permutation group. And in particular, if it's of finite order, then G is isomorphic to some subgroup of specifically Sn, where n is the order of G. And the way you want to think of that, and what I was trying to illustrate through this example that we'll talk through here in a second with D3, is that the group can act on itself, right? So the idea is left multiplication. So the Cayley table, right, when you're multiplying, we're looking at what happens, and you can physically see like where left multiplication by an element sends all the other elements. And so, you know, if I take some little g in G, then I can define LG as a permutation. Remember, a permutation is a one-to-one and onto function of the set G, where LG of H is just left multiplied by G, so it's just GH. So it's kind of similar to what we did with conjugation, right? Except for here we're not doing the inverse on the right. It's just left multiply. So through this left multiplication, you can view little g as permuting or reordering all the elements of the group G, right? Because think about the Cayley table. When you left multiply by an element, we know that in each row and column, every element shows up exactly once, right? So you're really just like reordering all the elements, right? We started with like E, R, R squared, S, SR, SR squared, but after we did R, we reordered it to R, R squared, E, SR squared, S, SR. And so in that way, we are thinking of the elements as permutations on this set, in this case of order 6. So here we're viewing R as some element of S6. Does that general idea make sense? Because judging from what I was seeing on the homeworks, I think this was fairly confusing when you guys were reading through it in the book. So that's not surprising. This is a little bit more abstract. So definitely ask questions if you have them. Okay. Well, I mean, we'll be doing this for a little bit because we're going to go through this example first, then we're going to use that to kind of help us actually prove the theorem. So let's look at this example first. So basically, right, my suggestion to you in the reading was to just label these elements with numbers, right? Because we usually think of S6, we've been using like cycle notation stuff. We think of it as like reordering the elements 1 through 6, right? Things in position 1 through position 6. And so all I'm saying is like this is 1, 2, 3, 4, 5, 6. And then we just want to see what does it do, right? So E, well, E doesn't do anything, right? It sends 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and 6 to 6. So it's still just the identity permutation. But then what does R do? So R is 2, right? And then, so R, if I left multiply by R, what am I doing to my original order? So I have turned 1, 2, 3, 4, 5, 6 into R, R squared, E, and then SR squared, S, SR. So if I want to write this in cycle notation, what has happened? So 1 went to 2, 2 went to 3, 3 went back to 1. Closes it off. 4 goes to 6, 6 goes to 5, 5 goes to 4. I close it off. So now I have written R as an element of S6 in nice cycle notation. And that's exactly from where does it send things when I left multiply by it. Questions on that? So why does 4 go to 6 instead of 5 again? Yeah, so notice here that 4 is S, right? So I'm looking at this column, and S was my 4, and where does R send it? RS is SR squared, and SR squared is 6. So my 4 turns into the element 6 there. And then I would look at 6 next, right? 6 is SR squared. It goes to SR, which is 5. So 6 goes to 5, and then lastly, SR goes to S, and so 5 goes back to 4. Does that make sense? Cool. Okay, And so then r squared, we see, so again, e goes to r squared. So I'm not going to necessarily write it like this in general, but okay, so 1 goes to 3, e went to r squared went to r, which is 2, and r went to e, which is 1. That closes off. S goes to sr, which is 5. SR goes to SR squared, which is 6, and then 6 goes to 4. S, and by the way, we should check, right? Does this make sense? What is the order of these things? We know R and R squared are order 3, right? These are products of two disjoint 3 cycles. We know that the order of a product is equal to the LCM of their orders, right? So this would have order LCM of 3 and 3, which is still 3. So like we're getting order 3 things out here. So that's good. The reason I say that is S should be different, right? S should be order 2. So we might imagine that it breaks down into transpositions as opposed to 3 cycles. And we'll see that that is true, right? So E goes to S, so 1 goes to 4. R goes to, wait, did I write this wrong? Oh, no, I'm left multiplying. Just kidding. SR. Cool. R goes to SR, so 2 goes to 5, and then we're only left with 3 and 6, and they do go to each other. R squared goes to SR squared. We're good. So this is 1, 4, 2, 5, 3, 6. SR, so, I mean, we always know the first one, like 1, the identity goes to SR, which is 5. R goes to SR squared, so 2 goes to 6, and then 3 goes to 4, and then our last one, you could pretty much fill in the blanks. It's kind of the ones that are not here, but we can look again. So R goes to S, so 2 goes to 4, and then R squared goes to SR, so 3 goes to 5. And so D3 is isomorphic to the subgroup E 1, 2, 3, 4, 6, 5, blah, blah, blah. I'm not going to write them all down, but basically all of these, right? Down to 1, 6, 2, 4, 3, 5. And this is a subgroup of S6, right? It lies inside S6. And it's not a permutation group, it's not a symmetric group itself always. In this case, it actually is isomorphic to it, although it's not clear from how it's written. But like D4, for instance, is not a symmetric group, right? Because D4 is order 8, and 8 is not anything factorial. So that one like is strictly a subgroup and could not be written as a symmetric group itself. This one can. D3 is also isomorphic to S3, right? We've seen this many times before. We've seen the two different Cayley diagrams, or Cayley graphs that make this pretty clear, right? We have the hexagon when we generate by 2 order 2 things, and we have like the triangle inside the triangle if we have an order 2 and order 3. But how can we see this? Well, that's because we don't have to just view left multiplication. So that's something that works for any group, because not every group has like a very obvious geometric thing that they act on. But D3 we know acts on the triangle, right? And like that's how we defined it. It's the symmetries of the triangle. And so if you do this, right, and I'm going to let S be the reflection across this just because I want S to be 1, 2. You can have it be whatever reflection you want. So here, what does R do? Well, R rotates it clockwise. Right, so E does nothing. Cool. R sends 1 to 2, 2 to 3, 3 to 1. Just by rotating, right? You see what vertex goes to what vertex. R squared sends 120 degrees. I'm kidding, 240 degrees. I know how math works. So this 1 goes to 3, 3 goes 240 to 2, and 2 goes 240 to 1. Okay. S, so the way I've drawn it, it just flips these two, but 3 stays fixed. So it's like 1, 2. SR means you do R first, right? So I rotate, so like where does 1 go? So for SR, 1 goes to 2, and then I flip it with S, right? So this is my R, this is my S, and it goes back to 1. Same with 2. Well, no. So 2 goes to 3 under R, and then 3 is fixed under S. And then 3 goes to 1 under R, and 1 goes to 2. And so this is exactly 2, 3. And then SR squared is the one thing left we know is 1, 3, but you can also see it because SR squared here, right? Like 1 goes to 2 under, 1 goes to 3 under R squared, and then that is fixed. 2 would go to 1 under R squared, and then that would get flipped back to 2 under S, and then lastly 3 goes to 2, which goes to 1. So essentially we have these two like different natural ways to look at D3, and my main point here and like why Cayley's theorem is useful and like why like the Cayley table is useful is that we don't always have this natural action, right? So like some of them you do. You can think of like V4 as acting on a square because you have the horizontal reflection and the vertical reflection. But you know, if I just hand you a random group, you're not going to be able to just easily find an object that it acts on, right? If I just hand you some random group of order like 36, you're not just going to be like, I understand. It's definitely going to act on like the, you know, dodecagon via this thing or something, right? It's going to be hard. And so this is why we have this very generalizable process, because we always have the notion of left multiplication in our group. Okay? All right. So let's prove Cayley's theorem. I know the book said, like, we're not going to prove it. We're going to prove it. It's an important theorem. The reason why it's important is this really shows us how much symmetry in groups are really inextricable from one another, right? Like the very first day I said, like, groups are all about symmetry. I mean, this theorem really shows that that is absolutely true. Every single group can be represented as a permutation group, right? Can be viewed as some subgroup of a symmetric group, which are inherently symmetries, right? You know it's true because it's in the name. So it's very important there, and you know, if you would go on in group theory a bit and start learning about group actions, you would see like more how this is true, and that this left multiplication is just like a very simple example of a group action. But anyway, yeah, this is like historically very important. It's not necessarily applied in a lot of places. So in terms of like our big capstone theorem, that's more Lagrange's theorem because of how useful it is. Cayley's theorem is more something that like gets at the inherent like structure of groups and like what they are really about. So it's more in like defining groups and talking about their essence and less about actually applying it. Okay. So we're going to mostly look at like the finite case, I guess. But basically note that this works for any group because you could just take the permutation. We just haven't talked about permutations of general sets, but you could imagine there's something called like S infinity, or like you can just take permutations of any number of objects even if it's infinite. And so this actually works for anything, but for us, let's just assume that G has order n. And what we want to show is that G is isomorphic to some subgroup, some H, where H is a subgroup of Sn, where n is the order of G. So we're going to do this in a few steps. So first I need to figure out like what H this is going to be. And as I mentioned before, I mean what we're really doing is left multiplication, right? And if I have a subgroup of a permutation group, what I'm really talking about are one-to-one and onto functions, right? That's what a permutation is. So any element of Sn is, and really that's coming from the order being G, so I'm going to just show that it permutes the elements of G. So is a one-to-one onto function on a set of order n. And so here, my elements in H are going to be exactly those functions I talked about earlier, the left multiplication functions for any G and G. So view LG as a function from the group to itself, where LG of H is GH, right? So it's, L is just for left here, right? So all I'm saying is we have a function from G to G. It's left multiplication by that element G. This definitely does still lie in G, right? G is closed under multiplication, so like GH is always still in G. I'm definitely getting another element out, so this makes sense. So I need to do a few things here. So we really have like 3 steps. One, I have to show that LG is really a permutation. So I need to show LG is 1-to-1 and onto. 2, I claim that this H is a subgroup of Sn. I need to actually show that H is a subgroup. And 3, I have to show that G is isomorphic to H. Right, so it's these three steps, that we truly have permutations, so we lie inside Sn, that it's a subgroup, so it's a subgroup of Sn, and then that G is isomorphic to it, so that we get our result. And definitely ask questions if you have them. I'm still looking at chat. Okay, so LG being 1-to-1 and onto, it follows pretty quickly from how groups work and multiplication, right? It's essentially the fact that every element shows up exactly once in each row and column in the Cayley table. But we can be more explicit. So my step 1. So if I want to show it's 1-to-1, right, assume LG of, say, H1 is equal to LG of H2. Well, this means exactly that GH1 is GH2. But we're inside a group, so we just have, we can cancel these with G inverse. And so H1 is equal to H2, so it's 1-to-1. That was supposed to be a check mark, and yeah. Cool. Okay, why is it onto? Well, start with some random element in your group. What do you need to left multiply by? Right, so I want LG of something equals H, right? That would give me onto. What should X be? Well, you can just solve for it, right? So this would mean GX equals H, so X should be G inverse H. And that is exactly right. Then H is LG of G inverse H. And that's just because, right, like G times G inverse H, well, your G and G inverse cancel and you get H. So it's also onto. So these really are permutations. We're really getting a reordering of our elements of G. No 2 things are going to the same thing. Nothing is missed. It's a perfect reordering. So our next is to show that H is really a subgroup of Sn. And what I'm really showing is that H is a subgroup of what's called like the symmetric group on G, because Sn is technically like, probably the functions on the set 1 to n to itself. But since G is order n, I'm basically just saying the 2 are the same. They are isomorphic. It's basically the same thing you did up here where we relabeled these elements by 1, 2, 3, 4, 5, 6. That's what allows me to say this is Sn. Okay. Well, here we can do the subgroup test, right? So we want to show it's non-empty. We want to show it's closed. We want to show it has inverses. So clearly it's non-empty because G is non-empty. So like I have L sub G's that exist, right? So H is non-empty since G is non-empty, right? So like E is in G, so LE is an element of H, right? We can always left multiply by the identity at the very least because the identity exists. So it's non-empty. What does it mean to be closed? So for closure, we want to take L, say G1 and L G2 in H. And then we want to see, is there product in H? And product meaning function composition here, right? These are functions. So that means we need to write LG1 composed with LG2 as L sum something, right, for it to be inside H. Well, what are we really doing, right? So LG1 composed with LG2 of H is, well, we first left multiplied by G2, and then we left multiplied by G1. But our group's associative, right? And so this is G1, G2 times H. And so really what we've done, if we just left multiplied by G2, then G1, we've just left multiplied by G1 times G2. And so this is LG1, G2 of H. And so this X up here is G1, G2. So it is closed, right? This guy is still in H. Just more specifically, LG1 composed with LG2 is LG1, G2, which is in H. So basically you just kind of track down, like, what is this left multiplication twice in a row? Well, it's just left multiplication by the product. What do you think the inverse is going to be of LG? If you had to guess using group knowledge. Any ideas? So it has to be L sub something, right? What do you think it's L sub? Left multiplication by what element would invert left multiplication by G? Yeah, so it's LH where H is G inverse. Right, and so we can just check this. So LG inverse composed with LG of H is G inverse GH equals H. Cool, so it's the identity. And LG inverse of H is G inverse H, which is also H. And so LG composed with LG inverse is the identity function. And so these are truly inverse functions, right? They undo each other. So they are inverses in the permutation group. And so this guy is in H, and we're good. So H is definitely a subgroup in that case. And so our last thing, finally, is that we want G to be isomorphic to H. And I mean, what do you think this goes to, right? So like I'll define phi from G to H. Well, phi of G probably should go to left multiplication by G, right? I mean, I have subscripts that have the elements, like this should seem like a very natural map after, once it's defined, right? Once H is defined. So we'll show that this is homomorphic one-to-one and onto. So onto should be pretty clear, right? So onto, you take a general LG and H, because that's what all the things in H look like. Well, that is exactly phi of G. So we're good. So onto is the super easy one there. What about one-to-one? Well, suppose phi of G1 equals phi of G2. Well, that means that LG1 is equal to LG2 as functions. Right, so if I say two functions are equal to each other, that means that no matter what input you give them, they have the same output, right? And so this means that LG1 of X is equal to LG2 of X for all X in G. Actually, I've been using H, so I don't know why I switched suddenly. LG2 of H for all H in G. Well, that just means that G1H equals G2H. And then we can right cancel. So G1 must be G2. And so We had that phi of them were equal, implies that they are equal, so we are 1 to 1. And then the last step is homomorphic, right? So if we look at phi of G1 times phi of G2, well, this is LG1 composed with LG2. But what was this equal to? We showed this above when we were checking that we had a subgroup and we were doing closure. What was LG1, LG2 equal to? LG1, G2, exactly. And this is exactly phi of G1, G2. And so it's homomorphic. And thus, we have an isomorphism. So I mean, like, I'm not expecting you in the future to necessarily like have this proof memorized or be able to do it by yourself. You know, this is somewhat involved, but I do think it's important to see just because it is like a very seminal result in like your first group theory course. I think it's something that like every abstract algebra 1 student should see. Because I think it really gets at the essence of what groups are all about. And Cayley was a smart dude. It's like the third thing we've seen attributed to him, right? Cayley graphs, Cayley tables, and Cayley's theorem. Smart dude. All right, any questions before we cut stream? I'll be around this afternoon. I guess, you know, basically starting at 1, my Calc 2 class has an exam, so like they will get preference if they have clarification questions, but I can help out with the problem set this afternoon, and again, I can help out with outlining your project if you are at the point where you're thinking about that. No questions? Okay. Well, I'll be in Discord if you need me. Otherwise, have a really good weekend.